So moving on. So this is how I started this thing, right? I love this picture. I love the album. I love the band, Pink Floyd, and all of the awesome Pink Floyd covers out there. But there's some real physics going on with this picture. Maybe you knew that already. But we call this refraction, okay? And this is the bending of light waves when they pass between medium of different density. So in other words, like on the other side of this prism, it's air, but within this prism, it's typically quartz, okay? So those have much different densities, and as a result, the light travels a different speed. It actually slows down a little bit in this more dense medium. And what that does is it separates those wavelengths of differing energy. Okay? And so this allows you to see that white light is actually composed of Roy G. Biv, the electromagnetic spectrum, okay? Or at least the visible portion of the electromagnetic spectrum. So this phenomenon is also observed in water, right? If I have a cup of water, or I don't have a clear glass of water, that would have been a smart thing to do, right? But if I have a clear glass of water and you put an object in it, you know, like you put a stick in something, maybe you've noticed this before, where like the object appears to be displaced. That's because of this refraction, okay? So a couple more things to discuss with photophysics here. So this is interference, and interference, we're going to see several manifestations of interference in this chapter and why and what makes that important to chemistry. So when we start adding light waves together, okay, if they have the same frequency, as you can see here, and those are aligned, okay, so we call this coherent radiation, okay? So, or another way to call that would be in phase. So the peaks and the troughs are lined up, okay? Then what we get is called constructive interference, okay? Interference. And so in other words, these two will add up and result in a higher amplitude, in other words, a brighter spot, okay? So what we would observe here is a brighter spot, kind of indicated by these points right here, okay? But now, what if these are out of phase? Out of phase. So, and now here in this out of phase picture, the peak is lined up with the trough, and the trough is lined up with the peak. This would give us total destructive interference, and it would result in no light at all, right? So that's kind of indicated by these darker spots right there, okay? And so there's actually some really cool applications of this. Your noise canceling headphones, right? They work by this principle. They work by making a complementary frequency of what's getting sampled, you know, all the ambient noise around you to the best of its ability, right? It's not a perfectly destructive interference signal that it creates, but all the same, it does create this complementary destructive interference signal that reduces the amplitude or the noise, the sound that you're experiencing. And certainly these devices also exist for light, for reducing the intensity of light as well, okay? So moving on, more photophysics to discuss here, okay? And so this is related to black body radiation, okay? So imagine we take this metal rod, let's say, and this is like probably an oxoacetylene torch, some crazy hot flame. And you probably know this already from your common everyday experiences. As you start heating this thing up, it glows. And you probably are familiar with the expression white hot, right? When you get something so hot that it's glowing white. Okay? So the reason for that is related to this principle of black body radiation. And the idea here is that all objects emit thermal radiation. So I'm going to write that down somewhere. All objects emit thermal radiation. And the energy or the wavelength or frequency of that thermal radiation is dependent on what temperature. So for example, here's an object that's 300 Kelvin. And so this, we know is room temperature, right? Also, that's approximately like a human temp. Technically, we're about 310 Kelvin. If you've got the Rona, you're maybe 314 Kelvin, right? Or the flu. But all the same, we're about this temperature. And these wavelengths, 10,000 nanometers or so, that actually corresponds to IR, infrared. So if you were to turn all the lights off right now, and you had some fancy infrared cameras, you would see me glowing. You would see me emitting thermal radiation. And that just so happens to be infrared thermal radiation. And this is where a lot of people get this wrong. A lot of people talk about how IR is heat radiation. And that's true, but it's misguided. All radiation is heat radiation. Gamma, X-rays, UV, whatever. It's all heat radiation. Because the hotter the object gets, so you notice these curves now, I heat something up to 500 Kelvin, and then 1,000 Kelvin, right? And if you notice here, 1,000 Kelvin, it would be glowing just barely red, okay? So I could actually look at this object and tell you that this object is roughly 1,000 degrees Kelvin just by the fact that it's emitting red light. Or think about your electric stove, right? Your electric stove, when you turn that thing on and it starts glowing red, that's because it's like 1,000 degrees. And now you notice here, when you get it even hotter, let's say around 2,000 degrees, look, it's emitting all of the visible wavelengths. And because it's emitting all of the visible wavelengths, it appears white. It's got all of the colors. So this is the origin of the term white hot. Something is so hot, it's emitting all of the wavelengths. Okay. Well, as it turns out, 6,000 degrees here, this is the temperature of our sun. The sun is 6,000 degrees. And that's why our sun predominantly appears yellow, because you notice yellow, the yellow color here is kind of right at the peak of this curve, okay? And you also notice the sun emits some UV and it also emits some infrared. So we get a boatload of EM radiation from the sun because it's so hot, okay? So the next time you're sitting around a campfire and you see those coals really glowing that beautiful red, almost orange color, you know now that those things are like 1,500 degrees, possibly even approaching 2,000 degrees if you've got a really raging hot fire going, okay?